Good morning, chemistry. All right, in this video, we're going to be using this worksheet, which is the same one we used, this worksheet 5, same one from reaction types. And I'm going to show you how to balance some of the different kinds of reactions. After we do the first two, I'm going to show you a trick, or two tricks actually, that you can use to simplify some of the more complicated ones. One of those tricks we will be using for combustion. The other one really will only help you if you have learned your polyatomic ions. If you don't know the polyatomics, it's not going to be quite so helpful for you. But those of you who have will find this extremely helpful. So we're going to start with reaction A, just like we did before. I would encourage you to write it out on a sheet of paper before we actually start. And I will show you what I mean here in just a moment by writing it on the board. So that's it. Let's get started. Okay, so I've written the reaction out on the whiteboard, just as it's written up here, except I eliminated these little parentheses because they don't actually matter for what we are doing. They are extra information that we don't need. So we're going to use this to balance. Now, to balance this, the first thing that we have to do is put a 1 in each of these three blanks, because what we are trying to do is get these coefficients down. And I'm getting a little ahead of myself, so I'm going to backtrack a little bit and tell you two things that you have to keep in mind when balancing. Number one, never, ever, ever, ever change subscripts. If you change the subscript, you're changing the chemical formula, which changes what the compound is. And the balancing is not going to be correct. You cannot change these. Okay, you are only allowed to change the coefficients, which are the larger numbers which go in the blanks in this. And that's what we are trying to determine, is what the coefficients are. So we'll be identifying or calculating those coefficients, and then from there we will be moving on to the next one, because that's really it. We're just trying to calculate those coefficients. So let's talk about how to do this. So we start by assuming that all of our coefficients are going to be 1, because we need at least a 1 there in order to actually do anything with it. Now, what I want you guys to do is make a table for each of these. And you do not have to use this after this reaction. You only have to do it on this one, because I want you to actually see if it is useful for you. If you don't like this, if this is confusing for you, if this just makes things more complicated, don't use it. Okay, but this is extremely helpful for most of these, especially when we get to combustion reactions. Combustion reactions can get fairly confusing, and this table is extremely helpful for that. So the first column is the reactants. The second column is the products. And we're going to have a row for every element that is present. Now, there are only 2 elements in this reaction, copper and oxygen. So we're going to have copper on the first row and oxygen on the second. Not O2. O2 isn't diatomic. We don't want O2 in this. We just want O. And then we're going to make a note of how many of each of these are in here. So for the reactant side, remember the arrow separates the reactants from the products. So on the reactant side, we have 1 copper, and we have 1 times 2 oxygens, so we have 2. On the product side, we have 1 copper and 1 oxygen. That's where we start. Now notice I wrote these on the far side here. That is so that as we go, we can cross them out and write the new number next to it. That's a good handy way of keeping track of what you have done, and to prevent you erasing a hole in your page if it takes you a little while to get through one of these. Now what we need is we need these 2 numbers to be the same and these 2 numbers to be the same. All of them do not have to be the same, just the rows. So these 2 need to be the same, and these 2 need to be the same. Well, these 2 are already the same. We have 1 and 1. These 2, however, are not. We have 1 and 2. There is nothing we can do to reduce this 2. It cannot go down. So we have to increase this 1 in order to balance this. And we can only have whole numbers in these. We can't go up to 1.5 or 2.3. It has to be a whole number. So the first question is, remember, this table reflects what this equation says. So as we change coefficients, it's going to change the information in the table. So we have to update the table every time we update the equation. So we need to increase this number. Well, the only way to increase this number is to increase how many oxygens there are on the product side. So we need to change this. Well, if we need 2 in order to cancel what's on the reactant side. So if we replace this 1 with a 2, that will give us 2 coppers and 2 oxygens. So both of these will go up to 2, which fixes oxygen, but it messes up our copper. So we need to now go back to the reactant side and find copper, and we need to fix this. Well, a 2 will fix this just as well. And so that's going to make these 2 the same and these 2 the same. This 2 does not affect oxygen because there's a plus sign separating them. This is 2 separate formulas, whereas this is just 1 formula. That's why this 2 only affects the copper, while this 2 affects both. So 2, 1, 2 would be our answer. So what you need to do then, after you get to this point, is go back to the worksheet and write in 2, 1, 2. And then that's it. Then you go on to the next one. Composition and decomposition reactions are extremely similar. You should be able to use this to balance both of those. So what I want you guys to go ahead and do is go through and balance your comp and decomp reactions. And then after that, go ahead on to, or then come back here, actually. My brain's a little scattered. Come back here, and I will show you how to do a single replacement reaction. And then we'll move forward from there to double, and then we'll end with combustion. So take a crack at those, pause this while you do, and I will be right back. All right, this is single replacement. So for single replacement, I've grabbed reaction C and written it out already and filled in the table. Now, here is your tip for single and double replacement, your first tip. Find the most complicated formula in the equation and start with that one. So between Fe, H2O, H2, and Fe3O4, Fe3O4 is the most complex formula. So we're going to start with this one. And what we're going to do is we're going to assume that this one has to be a 1. Which gives us a solid starting point for this reaction. If we assume this has to be a 1, then we can balance iron and oxygen against this formula on this side. And that will get half of our reaction balanced right off the bat. So we're going to start there. So this means we're going to have 3 irons and 4 oxygens. So let's start with iron. So iron, we only have 1 over here. Whatever we write in this blank is only going to be multiplied times 1. So if we just replace the 1 with the 3, that's going to fix our iron. Iron is now 3 on both sides. Okay, so next would be oxygen. Again, oxygen doesn't have any subscripts, so whatever we write here is going to be taken times 1. If we put a 4 here, then that's going to give us 4 oxygens. But that also changes our hydrogen. 4 times 2 is going to give us 8 hydrogens. So then we just come back over to the product side. Well, we have another 2 here. What times 2 gives us 8? Well, that's going to be another 4. So that gives us 8. Same, same, same. And that's our single replacement. So 3, 4, 4, 1 is the answer to C. Using this, go ahead. This should be enough to do most of your single and double replacement reactions. except for K, L, and R. K, L, and R are more challenging versions of these reactions. K is a single replacement reaction. L and R are both double replacement. So I want you to do all of the reactions that you can from single and double replacement except for K, L, and R. And the next in the video, I'm going to show you how to balance L. I'm going to show you two new methods, two things you can do slightly different on this table. I'm pointing here. I started to point right here. There's nothing here. Two different ways we can do this table to make this a little easier. And again, one of them anybody can use. The other one, it's going to be a little confusing. If you got hung up on G, then this is what I show you here next is going to help you with G as well. So, that said, go ahead, work on your single and your double. Just skip K, L, and R. You should be able to balance everything else with what I've told you, except for combustion. So, pause this, do those, and come back in just a second, and we'll do L on the board. All right, this is L. Now, what makes this one so challenging is the fact that H and O are split in the reactant side and on the product side. All four pieces of this have a hydrogen and an oxygen in them, which makes it extremely difficult to balance because it changes, no matter what coefficient you change, you're changing your hydrogen and your oxygen concentration. So the first trick I'm going to show you is still using the same method with the elements, but all we're going to do is we're going to put a plus sign in the middle of the hydrogen and the oxygen on both sides. And instead of listing all of the hydrogens, which would be 8 on here, we're going to put the first reactant here and the second reactant here. So there's 3 in the first one and 5 in the second. Okay, then phosphorus, there is just 1. Nitrogen, there is just 1. And then oxygen is 4 plus 1. Okay, then on the product side, we have for hydrogen 2 plus 12. Phosphorus is going to be 1. Oxygen is 1 plus 4. And nitrogen over here is 3. Now, other than that, we use the same method that I just gave you on reaction C. We're going to assume that the most complicated one is probably going to be a 1 and balance everything against that. So first off, we need to put our 1s in here. Now, if this is a 1, then phosphorus should be good, because phosphorus is already a 1 on both sides. Nitrogen is 3 over here, and only 1 over here. So if we come to this side to fix this, we replace this 1 with a 3, and that's going to change our nitrogen to 3 and fix nitrogen. But that 3 also changes hydrogen and oxygen. And this is why the plus signs can be helpful. This is only in the second compound, so it's these two numbers that we are changing. So what we can do then is go, okay, we have 5 times 3, so instead of 5 now, this is 15. And then on oxygen, instead of 1, it's now going to be 3. So now our phosphorus and nitrogen are balanced, but our hydrogen and oxygen are not. Reactant side is higher because we have 18 here and 7 here, but only 14 and 5 here. Now, hydrogen and oxygen are the only two things that we need to change. Both of them are in this compound on the product side, so this is the one we need to change to fix that. Rather than trying to use hydrogen, because hydrogen's numbers are so much bigger, let's use oxygen. Okay, we know that over here we have 4 plus 3, and over here we have 1 plus 4. Well, if we could change this number to a 3, that would balance our oxygen out, because that would give us 7 and 7. So if we put a 3 right here, because this is a 1, if we put a 3 here, that's going to balance our oxygen out by giving us 7. 3 plus 4, 7. That's also going to change this 2 to a 6. 6 plus 12 is 18, which is the same that we have over here. So this is balanced, 1, 3, 3, 1. Now this is a useful tool, but when you have this many split elements, this table can get a little confusing as well, which is why I'm going to show you another option. Okay, and this is particularly helpful for, like I said, K, L, and R. Because K, L, and R all have this same problem, where you have a lot of stuff that's split up. And I know some of you breezed right through R, but that's great. But most people struggle with R just as much as they do with L. So what we're going to do is we're going to split these into cations and anions instead of into elements. Now, like I said, you have to know your polyatomic ions to do this. So first off, I'm going to erase these numbers. I'm going to use blue this time. I'm going to draw a line between the first part of the reaction and the second part of the reaction. Now you have to know, like I said, you have to know your polyatomics in order for this to work. We know phosphate is a polyatomic ion. And we know ammonium and hydroxide are polyatomic ions. This one's easy because we have phosphate and ammonium. That 3 is part of the ammonium, so the 3 has to be on this side of that line. Water is different, though. Water's a little bit of a pain, and that's because this is the first time we've run into the ionic formula for water. This is the formula everybody knows and is familiar with, H2O for water. This is the covalent way of writing water's formula. There's another way that is ionic. The ionic way to write water is HOH, or hydrogen hydroxide. Hydroxide is our polyatomic ion, and so this would be our split. And so with this method, we now list these on the sidebar here instead of listing individual elements. Now, H3 is not a polyatomic ion. Okay, so H is the actual cation here. 3 is just a counting subscript in this case. And we'll talk about what that means more in unit 3 or 4. Okay, so we're just going to put H. H is bonded to PO4. Then we have ammonium, NH4, and hydroxide, OH. Now here we have 3 hydrogens, 1 phosphate, 1 ammonium, and 1 hydroxide. Then over here, we're using this instead. So 1 hydrogen, 1 hydroxide, 3 ammoniums, and 1 phosphate. So right off the bat, our numbers are much smaller here than they were here, which makes this a lot easier to work with. We're still starting in the same spot where we assume this has to be a 1. This is still our most complicated formula, so we want to balance things against this. Phosphate isn't going to change because it's already balanced, just like it was before. But ammonium, we have 3 over here because of this subscript, but only 1 here. So if we replace this 3 with a 1, that gives us 3 ammonium ions. But it also gives us 3 hydroxide ions. So while fixing our ammonium, it messed up our hydroxide. Well, if we come back to water, we see the same thing. 3, 1, I'm pointing at the wrong spot. 3 and 1, and 3 and 1. So if we can change both of these numbers to a 3 by doing this, that will balance our reaction. So this will give you the same results, but with smaller numbers. But again, you have to know your polyatomic ions in order for this to work. So those of you who don't will probably find this easier, even though it's a little more confusing. This is going to be easier than trying to balance it with the old way, without the plus signs. Those of you who know your polyatomics, this is going to work better for you. So this should be enough for you to get K and R, since I just gave you L. And then that's just going to leave combustion. I'm going to do a combustion problem here on the board in just a second and show you 2 tricks that will help you keep your combustion straight. The first one is, since oxygen is split, you have to use the plus sign on this. This won't help you with combustion because there's no ions in combustion. It's a covalent reaction. Composition, decomposition, and combustion are all covalent reactions. The 2 replacements, single and double replacement, are ionic reactions, which is why they're balanced slightly differently. So that said, pause this, knock out K and R real quick, and then come back for combustion. And we'll work through a combustion problem and go from there. All right, let's talk combustion. Now, I've chosen reaction X, which is kind of far down on the list, and that's because of one particular challenge that X poses that the rest don't, which will become apparent momentarily. Now, I've already filled it out for the most part. I do want to point out this 0 right here. I've done this deliberately. Some of these organic compounds will have an oxygen at the end. And if that happens, it's very important that you split the oxygen on the reactant side as well as on the product side, or you're not going to be able to get this to balance properly. Specifically, it's a 3, I believe, on the one that I'm referring to, which means that you don't have to do the trick that's in this one because of the 3. So we have 15 carbons, 30 hydrogens, 2 oxygens in the second compound, which is why it's after the plus sign. Then over here we have 1 carbon, 2 hydrogens, and 2 plus 1 oxygens. Now, the number one most important thing you have to remember with combustion reactions is that you always save oxygen for last. Because it is split, you will save yourself a lot of trouble by saving it for last. And if you keep wondering why I'm staring at the back wall, it's because there's some weird noises coming out of the bathroom right now. I'm guessing they're working on the plumbing issues we've had the last couple of days. So since oxygen is split, we're going to save it for last. We are going to track it as we go. We're just not going to try and balance it right now. So we're going to start with carbon. Now, carbon and hydrogen are usually pretty easy to balance. We have 15 carbons all in one spot. Well, all of the carbon over here is also in one spot. So if we replace this 1 with the 15, then that will balance carbon. But it also changes this 2 to a 30, which is a little annoying, but that's life. So we have 30 oxygens plus the 1 from the water. Next, for hydrogen, we have 30 hydrogens, but only 2 on the other side. So whatever we put here, we have to divide by 2. If we have to divide it by 2, 30 divided by 2 is 15. So this is going to be another 15. By putting a 15 there, that gives us 30 hydrogens, but it also gives us 15 oxygens in the second compound. Now, here is the sticking point. 30 plus 15 is 45. That is a problem because whatever number we put right here, we're going to have to multiply times 2. Which means we can only have an even number of carbons on this side of the reaction. Now, this is not the case if there's an odd number of carbons in this compound, which is the trick on the other one and why you want this. But since this is an odd number, there's no whole number we can put here to balance against it. When that happens, the trick is to double all of the coefficients that you currently have down. So we turn this into a 2, this into a 30, and this into a 30. And that's going to double everything in the table now as well. So this becomes 30, this becomes 60, this also becomes 30 because we doubled it here, and this becomes 60. So our carbon and hydrogen are still fine. Now oxygen is going to become 60 plus 30, which is 90. Now that's a nice even number. We can get 90 right here. But we don't want to actually put 90 here because that's going to give us 180 oxygens after we multiply by 2. This number that we had before goes into this blank. And that's going to give us our 90. So X balanced is 2, 45, 30, 30. And I think these are the largest numbers you'll see on the worksheet. There is a question on the test, which will have slightly higher numbers. But that is it for combustion. I will step off screen or step to the side here so you can get a better look at it. If you have any questions, comment or email me. Send me a message on Parent Square. But this is how you finish your combustion reactions. For those of you who are not going to be at school on Monday, this is the last trick. And this is what we're going over on Monday. So, have a wonderful night. Remember, 3 quizzes and a test this week. So, come to school prepared. We're finishing up this unit. Next week, we're going to move on to Unit 3, where things start to get more critical thinking and less memorization, assuming you've memorized everything you're already supposed to know. So, have a wonderful night, a wonderful weekend, and I will see everybody back in class.